Have you ever thought about robots that could do any task you might ask of it? Cook food, flip laundry, put away dishes? Well, the physical intelligence team sure has. This was their first paper, and it goes over their research to make a generalist robot AI that can do any task. Not just one model for a specific task, any task. They specifically wanted to make a robot foundation model that would function just like a usual LLM foundation model does. It would have a bunch of broad skills, but could be fine-tuned to do any task from those broad skills with relatively little data. The model they made, Pi.0, is specifically a vision language action model. This model takes in images, text, and a vector of the robot's state, and it uses that as conditioning to generate actions. But this is not the first vision language action model, or VLA, to exist. So what does Pi.0 here offer us that the previous research of VLAs didn't? This paper's big contributions are huge cross-embodiment training and an action expert which generates the actions. All of these we will go into shortly. But first I want to briefly go over why we even have these vision language action models in the first place. At the heart of what's being done in this paper is behavioral cloning. Behavioral cloning is exactly like it sounds. We want the model we're creating to clone some behavior. Most of the time it is our human behavior, since we know what we are doing, but it could also clone other robots' behaviors as well if they are sufficiently okay at the task. And sufficiently okay is actually the key point here, not perfect. Due to the complexity of the real world, no matter how well a robot performs or takes actions, there's always going to be model errors or robot errors or whatever you have. If all you have are pristine, perfect, and flawless data trajectories where no mistake is made, what do you think is going to happen when the robot predicts something that's slightly incorrect and suddenly it finds itself off the golden path of absolute truth? Usually it flips out and performs badly. Errors leads to more errors and it spirals out of control. The way to generally fix this is to just get more data. You could have perfect data, but you should also throw in data where a mistake is made or things are done incorrectly, and then show how to correct from that so that the model knows how to correct itself. This idea of having perfect data and incorrect data mixed together to be able to perform behaviors is kind of a rough overview. This is more of a conceptual introduction to what behavior cloning is trying to solve. Professor Sergey Levine has great lectures going over behavior cloning from a more rigorous perspective, and I will link that below in the video description. If you know a little bit about reinforcement learning, you might wonder why we're not using that with robotics, since that would be able to actually learn from its environment. But there's actually quite a few problems with applying reinforcement learning just natively to robots. At the time of this paper's creation, behavioral cloning was the main path to success for these general robot policies. Things have changed a little bit since then, and we will actually be talking about reinforcement learning very soon. But for now, since we are doing behavioral cloning, how can we make a general model that is able to do everything we want? And yeah, you would just collect a ton of examples from as many different behaviors and actions as possible and throw it all into a model so that the model can just do it all. It's kind of an extreme oversimplification of what these vision language action models are doing, but that is the most basic way of thinking about it. While we could just train something like a transformer model on all of the actions that we have collected so far, other researchers have found much more intelligent ways to train a model to copy actions. This is where vision language action models come in. Past researchers had realized that vision language models are trained to capture semantic understanding of images and text, and that could actually give robots some idea of what they are doing. Vision language models do know what a cat is in relation to a dog, what a tool on a desk looks like, or how to contrast the meaning of two different pieces of writing. The issue is that these vision language models are not embodied in the real world. All of their understanding is abstract, and so, while they may understand what a tool on a desk is, they can't actually reach for it. This abstract semantic understanding from vision language models seem to allow these robot models some semantic observational grounding, so they are not purely responding to just raw camera images anymore. They are actually understanding what is going on in the scene they are acting in. And this leads us to Pi.0. So the physical intelligence team wants a general robot policy model, a robot policy being the actions a robot takes. So a general robot policy just means that the robot can take actions generally, model, papers. But after really working through and understanding the model a bit more, I'm actually going to show you my redrawing of how this model works and how it processes its inputs. So here it is. And let's just start at the top and go down. The inputs are from this huge cross-embodiment dataset. And what that means is that there's just many different types of robots doing many different types of tasks. The paper mentions that some of the robot configurations and the data they collected themselves, while some came from an open source dataset called OXE. As far as I can tell, this type of mixed training, where they have so many different types of robot configurations and data that they collected both from themselves and from this open source data set, was unique to this paper at the time of this paper's publishing, which was late 2024. So from this training data mix, to train the model, they needed 4 things from each robot and task the robot was doing. First, they needed the camera images of what the robot was actually seeing. Second, a text annotation of what task the robot was doing, what it was working on. Third, they needed the proprioceptive state of the robot, which is mainly just the robot's current joint angles, and this is to give the robot a sense of where it is. Just kind of like how you know where your arm is even if you don't see it. And finally, number 4, they needed a chunk of robot actions. The research paper has this action chunk contain 50 actions. So from the current time step of wherever the robot is at, you would need 50 actions that it takes in the future from there to make a chunk with. This action chunk drives what the model will be predicting. And I will get into the how and why of action chunk prediction as we get to the output of the model, but do know that it being a chunk of actions is actually pretty important. But for now, let's just say you have all these things from some robot configuration and some tasks the robot is doing. One more thing that you'll actually need to select sometime tau. Right now, let's just say that tau is 0.5. The action expert is a flow matching model. So tau is the flow matching time step, which I will put over here on the side. Don't worry if you don't know what flow matching is or what tau is doing at this point. I will explain more about it and more about tau later when we get to the action expert outputs. For clarity's sake, the input action chunk to the model here will be noisy due to this time step tau. The vision language model backbone will take the image, or images if it's a multi-camera robot setup. It'll take patches of the image and turn it into tokens, and then it will project those image tokens into the language embedding space. It will also take the text, tokenize the text, and put that into the language embedding space as well. If you have any prior experience making vision language models, even toy versions of them, you probably know how that goes. Then the output of that embedding process is a vector of fused image text inputs. The vision language model backbone here does put some constraint on the action expert, mainly in the number of hidden layers that are needed to be used. Since we are using this vision language model's pre-training, we're going to need to make sure that the action expert uses the same amount of hidden layers. But other than that, you get the freedom to choose what the action expert looks like. The action expert is also newly initialized here, so it's trained from scratch. This makes sense if you think of the vision language model backbone as knowing how to see, and the action expert as learning how to move. Since they are doing different things, you can set up the action expert pretty freely. And why I point this out is the authors of this paper explicitly note that since they have this freedom, they decided to reduce the size of the action expert to make it run faster. One of the ways they do this is by not having the action expert share the same embedding dimension size as the vision language model. The vision language model uses an embedding dimension size of 2048, and the authors constructed their action expert to use only 1024. The cube vector and the action chunk will instead go into the smaller 1024 embedding space. The flow matching time, tau, gets mixed into the action chunk by an MLP projection as the action chunk gets embedded. Once Q and the action chunk are both embedded, you can concatenate them together to get a single Q action embedded vector. So now you have these two separately embedded vectors ready to be processed. And the paper describes this processing as being done like a mixture of experts model, where each one of these vectors will get processed by their own experts as they go through the actual model. The fused image text goes through the vision language model, and the Q plus action chunk vector goes through the action expert. The overall model, containing the vision language model backbone and the action expert, is set up in the usual transformer fashion, where there is an attention block followed by an MLP to make up one layer of the model. Going into the attention block, the fused image text embedded vector gets projected into the keys, queries, and values using the vision language model's already pre-trained projection matrices. And here's the most important part of the attention blocks. The Q and the action embeddings get projected by the action expert's keys, queries, and values into the same keys, queries, and values dimension that the vision language model uses. Each embedded keys, queries, and values vectors get concatenated together. So now they are all just one long key, query, and value vector in the same dimension. Here, the first however many tokens will belong to the fused vision language model inputs, and the rest of the tokens will belong to both the Q and the action chunk embedding. Attention is done with a special attention mask, which the authors call blockwise causal attention. In this special mask, the fused image text embedding from the VLM can only attend to itself. The Q vector from there can only attend to itself and the fused image text embeddings. And finally, the actions embeddings can attend to everything, both itself, the Q vector, and the fused image text embeddings. The authors devised the mask this way because they don't want the vision language model's attention projections to get influenced by the actions. The vision language model was trained without ever seeing Q vectors or actions. And if you let those tokens influence the vision language model, then it'll move away from what it was trained on. This is a distributional shift problem, and so this attention mask is meant to stop that from occurring. Roughly, this mask helps the vision language model preserve what it already knows. But the important thing here is that the actions can attend to the vision language model's understanding and the Q vector. So that is the conditioning for its understanding of what to output. From there, the standard attention calculation is done with this mask. Then the long resulting output vector is split back into the tokens corresponding to the vision language model and the tokens corresponding to the Q vector and actions. Each of those token streams are sent to their respective output projections, and the attention block is done. After the attention block, each of these streams get added to their residual, like normal for a transformer architecture, and then they both go to their own gated MLPs, with the action expert gated MLP being smaller than the vision language model's MLP, since they can make the action expert's dimensions lower. So as you can see here, the only place where the actions actually get to interact with this vision language model backbone, which is providing all this contextual internet scale pre-training knowledge, is just through this attention layer as it attends to this vision language model's tokens. After it is done with this first hidden layer, it'll repeat this same similar sort of layer style for how many blocks are actually in the vision language model backbone, and then you end up with the two vectors at the end. At this point, only the embedded action vector is selected, and it is then sent through an output linear layer to project the actions back to their right dimension. This gives something in the right shape and dimension as an action chunk. And why I say it gives something is because we are actually doing flow matching here. So to be precise, this something is a vector field in the shape of the actions at flow matching time step tau. If you have never heard of flow matching, this is where I'm going to give a brief overview in the context of these action chunks. But it is worth actually understanding flow matching due to how much and how often they're going to be appearing in generative modeling. And I will include links to an MIT lecture below where they do a great job of going over these flow matching and diffusion style trainings for generative modeling. So for flow matching, if you know anything about diffusion, flow matching can be thought of as the more general version of diffusion. Flow matching tries to flow or transform one distribution to another. Usually flow matching is done to transform the standard Gaussian in high dimensional space into a high dimensional distribution that we actually care about. To have this transformation over that time be linear, all you have to do is just linearly interpolate between the Gaussian distribution and the distribution that we want over those time steps. To do this practically, first sample a time step tau. Since our target distribution here is the distribution of action chunks, to set up the linear probability path, we just need to take the ground truth action chunk from our data set and then interpolate it with a Gaussian at that time step. So now we have a noisy action chunk, and the noise here corresponds to how far along tau we are in the transforming process. If tau is 0, the noisy action chunk should be fully Gaussian. There's no original signal left. If tau is 1, it should just be the ground truth action chunk. And between those two extremes should be an interpolation of the two. Here's an example from the MIT class showing this for a variety of points. But just having a noisy action chunk is not enough, because there are many, many paths in high dimensional space, which can give an action chunk that looks like that. It is okay to set up the model to try to predict the noisy action chunk at time tau, and then keep having it predict the next denoise action until you're at the target distribution. This is essentially what diffusion does. But there is a better way to predict this action chunk. The flow matching paper researchers realized that instead of having the model set up to predict the noisy actions along the path, you can set up the model to predict the vector field of the path. This is essentially setting up the model to predict the path itself at time tau. Since a vector field tells you the speed and direction of all the points in the vector field, this would be the model predicting the flow of the path at time tau. It would tell the speed and direction of each point at that time. So let's say you train a model to predict the vector field for each time tau for some specific example. If you then gave the model the time tau and a purely Gaussian input, you can then have the model predict the vector field or flow for the input at that time tau. And if you keep incrementing tau, you will get the flow from the Gaussian distribution all the way to the target distribution. And this is actually what's being done during inference. Inference for this model uses Euler integration with the predicted vector field to take pure noise actions to clean actions. So for our case here in Pi.0, the action expert here outputs a vector field, which is the flow at the time step tau. For the untrained Pi.0, this is just going to output complete garbage. So to actually train the model to be a vector field is just to simply regress the predicted vector field onto the reference vector field, which is obtained by interpolating the ground truth action chunk with the Gaussian noise distribution. To me, this is pretty amazing as it turns generative modeling into just a regression problem, and I find that simplicity to be pretty beautiful. You need to clarify now that the tau in this paper is different from just using a simple linear time step counting up. Tau in this paper is a sample from a transformed beta distribution and is meant to prioritize lower time steps near 0. They mention in the paper that at low time steps is when the mean of the actions are predicted. You can roughly think of this as where the actions are located in their high dimensional distribution space. This is the starting point that later time steps then refine upon. So for flow matching, you can think of these low time steps as defining the broad path to take to the clean actions conditioned on the observations, and the high level steps as slightly adjusting the path to get it just right. If this broad path and refinement analogy does not make much sense, that's okay. I would highly recommend checking out the diffusion policy paper and the action chunking with transformers paper, as those papers can help clarify this concept a bit. But roughly what the authors are thinking here is that for action chunk prediction, it is much more difficult to predict the action chunk's mean conditioned on all of the robot's observations OT, because the observation is so informative about how the action should look. This makes learning the mean of the actions conditioned on the observations the hard part. So the authors emphasize these lower time steps from the transformed beta distribution and training so that the model can see these lower time steps more often and be able to handle this mean prediction challenge. It's an important note, but in the end, the model is still predicting a vector field based on the time step. Now that we have gone over what the model is predicting, let's recap the whole model so it can all hopefully be clear. The model gets images, text, and the proprioceptive state and calls these the observation. During training, the observation gets passed into the model along with the interpolated noisy action chunk and the time step tau. Inside the model, it's a mixture of experts-like architecture where the actions, proprioceptive state, and the fused image-text inputs go down different streams to where they'll be attended by their own experts. But during the attention layer, the action representations get to attend to both the vision language model representations and the proprioceptive state to know what information it is conditioning the vector field on. The model outputs a vector field, which is regressed onto the true vector field for that noisy action and time step tau. During inference, the model takes in all the same observational inputs, but now there is no ground truth action. The action chunk is pure Gaussian noise, and this noise is integrated over 10 integration steps using Euler integration, and that takes the action chunk from pure noise to clean data. They use 10 integration steps as a balance between quality and inference speed. This integration step amount, combined with action chunking, where one inference call produces 25 or 50 actions, means the authors can hit 50 Hz of real-time control from their model. But the model will need to be ran 10 times to get these 10 vector fields the noisy actions must be integrated through to become clean. Here, the paper does point out that the authors use a cached version of the observation representations for every call after the first pass through the model. Since the vision language model's representations won't change for the same observation, the authors note that they can just keep using the same first calculated representations for the next 9 model calls during inference. The output vector field will be the only thing changing depending on where the action chunk is in the denoising process. This greatly speeds up inference. Now that we have a model that can generate actions and run quickly, let's see what it can do. So as you can see, it does better than the previous vision language models from other researchers on these tasks: shirt folding, busing, and toasting. For previous vision language action models, OpenVLA tokenizes autoregressively and can't do action chunking at a high frequency. Octo can do chunks, but it has less model capacity. So Pi.0 is beating them with the ability to do action chunking and by having more capacity. Now, as expected from a foundational model, fine-tuning for a task does lead to better results than training for that same task with a model made from scratch. DP here stands for diffusion policy, and ACT is another similar action generation transformer. These models are task-specific so that they can only generate actions for one task that they have been trained on. And based on my troubles getting my diffusion policy implementation to work to pick up a cube, I'm not really shocked at these results. It's also worth noting here that altogether Pi.0 is 3.3 billion parameters, while the ACT model is about 80 million parameters. You get much better versatility and performance, but there is a size cost to using these foundational models, as you might have imagined. And finally, here at the end of the paper, the authors do note struggling to get a few tasks working reliably. And well, since this paper came out late 2024, The physical intelligence team has made some really good progress on the reliability of their models. They go over their improvements in subsequent research papers, and I'm actually going to go through and do a paper analysis on each of their milestone vision language action model papers. So if you found this video helpful in understanding their first vision language action model, please like and subscribe the video so you can follow along with me on understanding their entire series of papers. Thank you.